Welcome back, everybody. Ready for another deep dive?
Absolutely. Always ready to dive in.
Well, today's topic is something I know you, our listener, is really interested in the C++ algorithm library.
Oh, good one.
Yeah, they actually shared some documentation with us from cppreference.com. And I have to say, looking this over, this library is amazing.
It really is, yeah.
It's like having a Swiss Army knife, but for data manipulation.
Yeah.
Just incredible how many pre-built tools C++ gives us to handle common operations.
Yeah, and it's not just about convenience. I think what's fascinating about the C++ algorithm library is that it's about writing efficient, elegant code.
Right.
It provides a standardized, a generic way to perform operations on ranges of elements.
Okay.
So whether you're working with arrays or lists or any other container, these algorithms have got you covered.
So let's break down this idea of ranges, because it seems pretty fundamental to the whole library.
Yeah.
It's more than just saying a bunch of data.
Yeah. Absolutely. A range in C++ is an abstraction that represents a sequence of elements.
Okay.
And it's defined by a beginning and an end, which are usually iterators.
Right.
So this abstraction allows the algorithms to work on a variety of data structures,
Gotcha.
not just contiguous memory blocks, which is really useful.
That makes a lot of sense. So iterators are kind of like these pointers, these special pointers.
Yeah, exactly.
That help us define the boundaries of where the data is.
Exactly.
And that way the algorithms know, okay, this is where we start working, this is where we stop.
Yeah. That's precisely it. And because the algorithms are generic, they can work on any data type, as long as, the necessary operations.
Okay.
Like comparisons or arithmetic are defined for that type. So it makes the library incredibly versatile.
Yeah, that's pretty awesome. C++ really seems to emphasize reusability and avoiding unnecessary code duplication. Now, I'm looking through the documentation here, and I see some mentions of constrained algorithms introduced in C++20. What's the story behind those?
Yeah, so constraint algorithms are a more modern and expressive way to work with the algorithm library. They take advantage of concepts, also introduced in C++20, to enforce compile time constraints on the types used with the algorithms.
Okay.
So this leads to better error messages, it makes the code more robust.
So it's like having a safety net at compile time.
Yeah, exactly.
The compiler can actually verify that I'm using the algorithms correctly with the right data types.
Right.
That definitely sounds helpful.
Absolutely. And along with constrained algorithms, C++20 also brought us ranges, which provide a more composable and elegant way to express algorithms.
Okay.
You can chain ranges together, you can filter them, you can transform them, all with a very readable syntax.
So this ranges thing seems like kind of a big deal.
It's very powerful, yeah.
It feels like C++ is always evolving to become even more powerful and expressive. Yeah, absolutely.
Now, speaking of advancements, I also see that execution policies are mentioned. And these were introduced in C++17. I'm guessing this has something to do with how the algorithms are actually executed.
Yeah, that's right. Execution policies give developers control over how algorithms are executed.
Okay.
You can specify whether an algorithm should run sequentially, in parallel, or even in a vectorized fashion.
Okay, hold on. Parallel execution. Does that mean that I can easily make my code run faster by utilizing multiple cores?
It can, but it's not always as simple as flipping a switch.
Right.
Using execution policies effectively requires a good understanding of your algorithm, the data, and potential race conditions.
Sure.
But it does open up, powerful possibilities for performance optimization.
So a tool for more advanced use cases.
Yeah.
But incredible that C++ gives us, as developers, that level of control.
All right, I think we've laid a good foundation here. Now let's dive into the library itself. To make this manageable, how about we explore it by category rather than trying to cover every single function?
That's an excellent approach, yeah. Grouping the algorithms will make it, it'll make it easier to understand the overall structure and purpose of the library.
Perfect. Let's start with what the documentation calls non-modifying sequence operations. The name pretty much explains it, right?
Yeah.
We're looking at algorithms that don't actually change the underlying data. I see one called std.findiff. What's special about this one?
So std.findiff allows you to search for an element within a range that satisfies a specific condition.
Right.
which is defined by a predicate function.
All right.
So this gives you a lot of flexibility in how you search.
So like a customized search.
Exactly.
Instead of just looking for a specific value, I can define any condition I want.
Right.
Like find the first negative number in a list.
Exactly. You can easily search for elements based on, complex criteria. And then there's std.search, which, as the name suggests, lets you find a specific subsequence within a larger sequence.
So if I'm looking for a particular word or phrase in a sentence, std.search would be the way to go.
You got it. And, C++11 introduced several other useful functions in this category.
Okay.
There's std.allof, std.anyof, and std.noneof.
Right.
They efficiently check if a condition holds true for all, some, or none of the elements in a range.
Wait, those sound incredibly practical.
Yeah, very useful.
I can imagine using std.allof to quickly verify if, let's say, all elements in an array are positive.
Absolutely.
That would prevent me from writing a tedious loop.
Yeah, it can prevent you from writing tedious loops and make your code more expressive.
Yeah.
And speaking of avoiding loops, std.forEach, also introduced in C++11, provides a cleaner way to apply a function to each element in a range.
So these additions in C++11 seem to really focus on making the code cleaner and more efficient.
Yeah.
It's like C++ is saying, hey, we know you need to do these things all the time, so here's some elegant tools to help you.
You're catching on to the philosophy. Now let's shift gears and explore algorithms that actually modify the sequences they operate on.
Yeah, so now we're moving into modifying sequence operations, where things get a bit more hands-on.
Right.
These algorithms actually change the data within the sequences that they work with.
Okay.
So a classic example is std.copy, which, creates a copy of a range of elements.
Right. std.copy. That one seems pretty self-explanatory.
Yeah.
But what about std.transform? That sounds a bit more intriguing.
Yeah.
What kind of transformations are we talking about?
So with std.transform, you can apply a function to each element in a range.
Okay.
Essentially modifying the elements in place or creating a new transformed range.
Right.
It's incredibly versatile.
Oh, cool.
Let's say you have a vector of numbers and you want to square each one.
Okay.
std.transform can do that effortlessly. So it's like having a powerful mapping function.
Yeah, exactly.
That can apply like any logic I want to each element.
Right.
I can even use it to convert a vector of strings to uppercase.
Precisely. And it gets even more interesting.
Oh, wow.
You can use std.transform with two input ranges, applying a binary operation to corresponding elements.
Okay.
So this is useful for operations like element-wise addition or multiplication between two vectors.
Okay, that opens up a lot of possibilities. Now, what about removing elements from a sequence?
Yeah.
I see a function called std.remove.
Right.
But I'm always a bit wary because I know removing elements from containers
Yeah, it can be tricky.
can sometimes be tricky.
You're right to be cautious.
Yeah.
While std.remove appears to remove elements, it actually just shifts the elements to be removed to the end of the range and returns an iterator to the new logical end.
Yeah.
The elements are still physically present in the container.
Oh, that makes sense. So it doesn't actually erase the elements from memory. It just rearranges them and tells me, okay, this is where the useful part of the range ends.
Exactly.
What happens if I actually want to erase those elements?
So that's where the erase remove idiom comes in.
Okay.
You essentially use std.remove to get the new end of the range and then use the container's erase method to physically remove the unwanted elements from the container.
Okay, so it's a two-step process. First, rearrange with std.remove, then actually erase with the container's erase method.
Right.
I can see how not understanding this could lead to some subtle bugs.
Definitely.
Thanks for clarifying that.
No problem. Now, shall we talk about everyone's favorite topic, sorting?
Absolutely. Sorting is like the cornerstone of so many algorithms.
Yeah.
Everyone knows and loves std.sort.
Yeah, it's classic.
It's efficient. It's reliable. What's not to love?
It truly is a workhorse.
Yeah.
It's typically implemented using intrasort, which combines the best aspects of quicksort, heap sort, and insertion sort to provide consistent performance.
Wow.
But it's not the only sorting algorithm in the library.
Right. There's also std.stablesort.
Yeah.
I remember reading about that.
Yeah.
What makes it different from a regular std.sort?
So as the name suggests, std.stablesort guarantees stability.
Yeah.
This means that if you have elements with equal values, their relative order will be preserved after the sorting.
Right.
And this can be crucial in situations where the original order carries some meaning.
That's a subtle but important point.
Yeah.
Can you give me an example of when this stability would really matter?
Yeah, imagine you have a list of students sorted by their last name.
Okay.
Now you want to sort them by their GPA.
Right.
While maintaining the alphabetical order of students with the same GPA,
Right.
STD stable sort would be perfect for this.
Okay.
Because it ensures that the last name order
Gotcha.
within each GPA group remains intact.
That's a great example. So if the order of equal elements matters,
Yeah.
I should reach for std.stablesort instead of std.sort?
Exactly.
Got it. Now, once my data is nicely sorted,
Yeah.
I can use std.binary search to find specific elements super quickly, right?
You're absolutely right. std.binary search is designed for searching sorted ranges.
Right.
And it's incredibly efficient
Yeah.
with a logarithmic time complexity.
Right.
This means it can search through millions of elements in just a few steps.
The logarithmic time complexity. That sounds impressive.
Yeah.
We'll definitely have to delve deeper into the world of complexity analysis later on.
Yeah, we'll get to that.
But first, let's explore some of the less familiar areas of the algorithm library.
Okay.
What about heap operations?
Yeah.
I'll admit heaps are a bit mysterious to me.
Sure.
Can you shed some light on what they are and why they're useful?
So a heap is a specialized tree-based data structure
Okay.
that satisfies the heap property.
Right.
Every parent node is either greater than or equal to. In a max heap, or less than or equal to. In a min heap, it's children.
Okay.
This property allows us to quickly access the largest or smallest element,
Gotcha.
making heaps ideal for implementing priority queues.
So it's like a self-organizing tree.
Yeah.
Where the most important element is always at the root.
Exactly.
That makes sense for priority queues where you constantly need to retrieve the highest priority item.
Yeah.
What kind of functions does the algorithm library provide for working with heaps?
So we have std.makeHeap to create a heap from a range of elements.
Okay.
There's std.pushHeap to add a new element while maintaining the heap property.
Right.
And of course, std.popheap removes the top element, the largest or smallest, and reorganizes the heap accordingly.
Right.
These are all available from C++ 98.
Wow.
C++ 11 added some useful functions like std.isheap.
Okay.
To check if a range represents a valid heap, and std.heapsort to sort a range using a heap.
Wow. So these functions allow me to build, manipulate, and even sort using heaps.
Exactly.
Sounds like heaps are incredibly versatile.
Yeah.
All right, moving on. What about set operations? The name kind of gives it away.
Yeah.
But what exactly do these algorithms do?
So set operations in the C++ algorithm library are designed to work on sorted ranges.
Okay.
They allow you to perform operations like finding the union, intersection, and difference between two sets.
Right.
Just like you would with Venn diagrams.
So if I have a list of students enrolled in course A and another list for course B, I could use these operations to find students enrolled in both courses.
Yeah, absolutely.
Students enrolled in only one course, and so on.
Exactly. For example, std.xunion would give you a combined list of all students enrolled in either course. std.set_intersection would give you the list of students taking both courses.
Gotcha.
And std.set_difference would tell you which students are in one course but not the other.
Right.
These are all available since C++ 98.
That's incredibly useful for analyzing and manipulating sets of data. It's like having a set theory toolkit built right into C++.
It is.
All right, we've covered a lot of ground.
We have.
But I'm curious about the numeric operations category.
Yeah.
What kind of algorithms do we find there?
Yeah, so the numeric operations category focuses on algorithms specifically designed for numerical computation. A classic example is std.accumulate, which has been around since C++ 98. It's a very versatile function. Can be used to sum up a range of numbers or perform other kinds of reductions.
Okay, so if I have a vector of numbers and I want to find their total sum, std.accumulate can do that for me.
Exactly. You provide it with a starting value, which is usually 0 for summation, and a binary operation that defines how the elements are combined. For summation, you'd use the addition operator.
So it's like a generalized sum function. But you mentioned other kinds of reductions. What else could I do with std.accumulate?
Imagine you want to calculate the product of all numbers in a vector. You can simply change the binary operation to multiplication. Or you could concatenate a range of strings using std.accumulate with a string concatenation function. It's very flexible.
That's pretty cool. It seems like std.accumulate can handle a wide variety of scenarios where I need to combine elements in a specific way. Now I see another function called std.innerProduct. That sounds familiar from my linear algebra days. Is it related to dot products?
You're spot on. std.innerProduct, available since C++98, can indeed be used to calculate the dot product of two vectors. It takes two input ranges and two binary operations, one to multiply corresponding elements and another to sum up the results.
So it's like a specialized version of std.accumulate that's tailored for dot products.
Yeah.
You said it takes two binary operations. Why two?
So the first binary operation defines how to combine corresponding elements from the two input ranges, which is typically multiplication for dot products. The second operation defines how to combine the intermediate results, usually summation. This makes std.innerProduct more general than just dot products. You can use it for other operations like weighted sums or even to calculate correlations.
That makes sense. It's like std.innerProduct gives me the building blocks to define a variety of operations on pairs of ranges. This C++ algorithm library is truly a treasure trove of useful tools.
Yeah.
We've talked about a lot of specific algorithms, but I'm curious about your overall perspective. What do you think makes this library so valuable for C++ developers?
Well, the C++ algorithm library is really a testament to the power of generic programming. It provides a standardized, efficient, and reusable way to perform common operations on a wide variety of data structures. This promotes code clarity, reduces the risk of errors, and allows developers to focus on the higher-level logic of their applications.
Yeah, I completely agree. It's like having a collection of well-tested, optimized building blocks that I can use to assemble complex functionality without having to reinvent the wheel every time. Now, before we wrap up, I want to touch on something we've mentioned a few times: time and space complexity. Why is understanding these concepts so crucial when working with algorithms?
Time and space complexity are essential for analyzing the efficiency of algorithms. Time complexity tells us how the runtime of an algorithm grows as the input size increases. Space complexity, on the other hand, tells us how the memory usage grows.
So even though the C++ algorithm library provides highly optimized implementations, I still need to be mindful of how the performance might change as my data scales.
Absolutely. For small data sets, the differences in complexity might be negligible, but as your data grows, choosing the right algorithm with the appropriate complexity can make a huge difference in terms of both speed and memory usage.
Can you give us some examples of different complexities and how they might affect performance in practice?
Certainly. Let's take searching as an example. A linear search, where you go through each element one by one, has a time complexity of OAN. This means the runtime grows linearly with the number of elements. If you have 1,000,000 elements you'll need to perform, on average, 500,000 comparisons.
Okay, that sounds slow, especially for large data sets. What's a more efficient alternative?
If your data is sorted, you can use std.binary search, which has a logarithmic time complexity, denoted as O log n. This means the number of operations grows much slower than the input size. For 1,000,000 elements, a binary search might only require about 20 comparisons.
Wow, that's a huge difference. So sorting my data can often be a worthwhile investment if it allows me to use more efficient search algorithms later on.
Exactly. It's all about trade-offs. Sometimes it makes sense to invest time in pre-processing your data, like sorting it to enable the use of algorithms with better complexity. Other times, a simpler algorithm might be sufficient.
That's a great point. It seems like understanding time and space complexity is crucial for making informed decisions about which algorithms to use. Any final thoughts on the C++ algorithm library before we wrap up?
Well, the C++ algorithm library is a powerful tool that every C++ developer should have in their arsenal. Not only does it provide efficient implementations of common algorithms, but it also encourages a more expressive and generic programming style. Mastering this library can significantly enhance your ability to write clean, efficient, and maintainable C++ code.
Well said. I think this deep dive has been incredibly insightful. We've explored the core concepts of ranges, iterators, and generic programming, and we've seen how the C++ algorithm library provides a rich set of tools for manipulating data, from basic operations like searching and sorting to more specialized tasks involving heaps and sets. We've also discussed the importance of understanding time and space complexity to choose the right algorithm for the job. To our listeners, I encourage you to explore the C++ algorithm library further. You'll be amazed by the amount of functionality it offers, and you'll discover how it can make you a more effective and efficient C++ programmer. Thanks for joining us on this deep dive.